Hey everyone, Mr. Fransky here. Today we're going to be talking about indefinite integrals. So we talked about definite integrals before. Today, indefinite integrals, they just undo derivatives. It's not too bad. So students will be able to find families of solutions curves using the indefinite integrals. So really this is just a way to, say, take the antiderivative. And we're going to try it with lots of different things and learn lots of different methods to do it in this chapter. So we're just going to do an intro today. So some of the vocab you're going to have to know: indefinite integral, of course, antiderivative, and family of solutions. The last two are things we've seen. First one is the only really new vocabulary. So to warm up a little bit, I want you to try a free response question from 2012. And we can do A, B, and C. So if you want to try A, B, and C, you can. I will kind of go through A and B a little bit, and then C, I'll go through Euler's method. This is a no calculator problem. So give it a shot without a calculator. Do as many of the parts as you want. We can't do D yet. D is from chapter 9. We have that to look forward to. It's a good problem, but we don't have to do it for now. So feel free to give this a shot, and then we'll try it together. All right, so I'll kind of go through each part of the problem, but C is the part that I really want to make sure that we focus on. So if you want to skip to that part, you can. So for A, they ask us to write an equation for the line tangent to the graph at x equals 1. So for that, we need a point and a slope. Well, our point, we know the x-coordinate is 1. This table gives us the derivatives. It doesn't give us the y-coordinate, so they must give us some other information because they never ask us a question that we can't do. So let's see what they tell us in the top here, the part that you guys never read, right, that you should. Okay, function f is twice differentiable. F of 1 is 15. Oh, there we go. 1, 15. There we go. Okay, tell us f double prime of 1 is 20, so it's concave up at 1. They don't say it's concave up the entire time. It probably is between 1 and 1.4. The concavity probably doesn't change, but it might. Okay, so now we need a slope. Well, the slope we can get from the table because this is f prime, so the slope is 8. So we're going to have y minus 15 is equal to 8 times x minus 1. Now they want us to use that to define as a linearization equation to approximate 1.4. So plug 1.4 in for x. So we have y is equal to 8 times 1.4 minus 1 plus 15. So 1.4 minus 1 is 0.4 times 8 is 3.2 plus 15 is 18.2. There you go. Okay, so that's our approximation using the tangent line, using linearization. Next, they want us to use a midpoint Riemann sum to evaluate the integral from 1 to 1.4 of f prime of x dx. So we're doing two subintervals of equal length. That seems weird because there's 4 here, right? But look at what they asked us to do. They asked us to do midpoint. They asked us to do MRAM. So we have to use this as one interval, and this is one interval, and we're going to use the midpoint value to be the height of our rectangle, right? So if you were to draw a picture of this, here's 1, here's 1.4, here's 1.2, here's 1.1, and 1.3. So this determines the height of my rectangle, and the rectangle goes from 1 to 1.2, and then this guy goes like that, right? Okay, so to do that, so we want to approximate that integral. So integral from 1 to 1.4. Oh, my calibration's a little off. There we go. Of f prime of x dx is approximately equal to, let's see, so the width of that guy is 0.2. The height is going to be 10. Plus the width of this guy is 0.2 times the height of that, which is f of 1.3, which is 13. You can just circle that and be done with it, right? But 0.2 times 10 is 2, plus 0.2 times 13, that's 2 times 1.3, that's 2.6. So that would give us 4.6. Okay, so that's the integral value. Now I say to use that to approximate the value of f of 1.4. So the way we do that is we know that the integral from 1 to 1.4, f prime of x dx, we can use the antiderivative. What's the antiderivative of f prime? Well, it's f. So this is f of 1.4 minus f of 1. We don't know f of 1.4, that's what we want, but we know f of 1. F of 1 is 15. So we put 15 in there. Add it to our approximation. So 15 plus 4.6 is 19.6. Okay. All right, so now let's do Euler's method. So I have this on a new screen. All right, so we got Euler's method with 2 steps of equal size, and we are starting at x equals 1 to approximate f of 1.4. So let's make our little chart here. So we have our starting point, we have our slope, which in this case is going to be f prime of x. We're just going to get it from the table. That's really easy. And then we have delta x, and we have our delta y, which is m times delta x. And then we have our new point, which we're going to get by doing x plus delta x, and then y plus delta y. Okay, so our starting point, we're starting at x equals 1. Well, what's the y-coordinate? I think they gave that to us. Let's see, the y-coordinate, it looks like, is 15. So f of 1 is 15, so we start at 1, 15.
The derivative when x is 1 is 8. They give it to us. Awesome. So delta x, let's see, they want us to use 2 steps to go from 1 to 1.4. So that's 1 to 1.2 to 1.4. So it looks like our step size is going to be 0.2 each time. You're just doing 2 steps. So if it was 1 step, we'd do 1.1, 1.2, 1.3, 1.4, but we're just doing 2 steps. So the change in y is going to be m times delta x. 8 times 0.2, 1.6. If you want to do this in fractions, it'd be 8 times 1/5, which is 8/5. You can do it with fractions, but in general, they do this, they make it easy enough that you can do just 1 or 2 steps using decimals. So our new one is going to be 1.2, and then 15 plus 1.6 is 16.6. All right, so that's our new starting point, 1.2 and then 16.6. Our derivative now at 1.2, so it's kind of tricky there. You might try to trap you into using the 1.1. I may have done that on a previous recording of this video, but we're going to use the derivative at 1.2, which is 12. So then our change in x is 0.2 again, right, because we're going to 1.4 this time. So now if we multiply 0.2 by 12, so 12 times 2, the way I do decimals, right, 12 times 2 is 24, and then 12 times 0.2 then would be 2.4. So it's 2.4 right here. So now we have 1.4, and our y plus delta y is going to be, let's see, 16.6 plus 2.4, that's 19 on the button. Okay, so f of 1.4 is approximately 19 using Euler's method. So you see we did this with 3 different methods, right? We did it with linearization, we did it with using an antiderivative or an integral approximation using MRAM, and now we've seen it using Euler's method, and they all were kind of in the same ballpark, right? We got 18.2, 19.6, then the Euler's method kind of split the difference at 19, but all different approximations, and none of them is probably exactly accurate, but they're going to be close, and they're going to be good approximations, and that's kind of what we're aiming for here. So they told us that f prime, or f double prime of 1 is 20, so that'd be a very steep concave up function. I don't know what happens after that. It's probably still concave up over here, which would mean that Euler's method would be an under approximation, because the tangent lines would be underneath, but we don't know that for sure.
All right, so what's an indefinite integral? So what we talked about before is a definite integral. Definite integral from a to b of f of x dx. And we found an antiderivative, f of b minus f of a. And this gave you the area under the curve, f of x from a to b. Right? That's the whole point of a definite integral. So you don't have to use antiderivatives. If it's like a semicircle or something, you can just find the area. Remember, this is area above minus area below. That does not necessarily represented by the f of b and the f of a, but it does it for you, right? So if you have parts that are above and below, it's going to do that automatically for you, right? So it'll find you the change in the antiderivative. So indefinite integral, all this is saying find me the antiderivative. So if I just have it with no limits on there, it's just telling me find what the antiderivative is and then add a plus c. So why don't we have to have a plus c over here? Well, you could use it, right? We talked about this before. F of b plus c minus f of a plus c. This plus c's would just cancel out, so we don't have to worry about it over here. But over here, they're saying, find me the family of solution curves. And then you could use that to find the definite integral, right? But antiderivative is just saying, just do the indefinite integral, find the antiderivative. That's all they want. And then make sure you have the plus c because it has to be generic. So remember from fundamental theorem, if you take the derivative of the left side, dx, right, dx up there, it should be the same thing as the derivative of the right side. Capital F of x plus c. Well, the derivative of the antiderivative is just f of x. And the derivative of the antiderivative over here, also f of x, right? And the c goes away. Okay. All right, so examples. So antiderivative of x to the negative 2, that's 1 over x squared. But we do the antiderivative as we did before. We just add 1 and divide by the same thing. So this is going to be x to the negative 1 divided by negative 1. Another way of writing that is negative x to the negative 1, or negative 1 over x, and don't forget the plus c. All right, next one, antiderivative of sine x plus e to the x. The antiderivative of sine is negative cosine, right? Because the derivative of cosine is negative sine, so we have to have a negative to cancel that out. And then plus e to the x. E to the x is its own derivative, plus c. That's it. All right, this guy, I'm going to rewrite that because you guys don't like the dt on top. I know. You can just slide it off if you don't like it. So we have 1 over t squared plus 1 dt. That's the derivative of what function? I think it's tangent inverse. That's tangent inverse, whoops, of t plus c. That's it. So Lots of practice with our derivatives, right? Those derivatives that we saw back in chapter 3. So some rules that you already know. One of them, so we know the derivative of x to the n is n times x to the n minus 1. So in that case, the antiderivative of x to the n dx is going to be x to the n plus 1 divided by n plus 1 plus c, because if you take the derivative of the right side, the n plus 1 will come to the front, it has to cancel, and then this will be reduced to n. So you just have to make sure you divide out that n plus 1. All right, so that's one of them. Some other stuff that can be handy. The antiderivative of k times f of x dx, you can just pull the k out, right? We've talked about this before. You can always just pull out a constant. So this is especially useful for fractions. So if you have like the antiderivative of like x to the 6th over 5, something like that, dx, pull out the 1/5, integrate x to the 6th, and then just worry about the 1/5 later. Okay. So you pull it out, and then you just have integral f of x dx. Okay, so just take the antiderivative of f of x multiplied by k. And then, of course, if you have an addition, f of x plus g of x, we really used a lot of these on the last slide, actually, dx. You can just split it up. Integral f of x dx plus integral g of x dx. Those are kind of the big ones. Now, this only works if n is not equal to -1. Because if n is -1, this would be x to the 0 over 0. That's not happy. Okay, so what the heck happens if n is -1? It's a little bit tricky, right? So let's think about what that would be. That would be the integral of x to the -1 dx. That is the antiderivative of 1 over x dx. Now, the reason this is tricky is because you guys are probably screaming at the screen. It's a natural log, right? Natural log derivative is 1 over x. Yes, but the tricky thing is 1 over x is defined on two sides. Right? This is 1 over x. Okay? And natural log is only defined on the right-hand side. The problem is we need an antiderivative for the left side of 1 over x, right? So the slopes, let's think about the slopes. The slope at +1 is -1. Slope at -1 is -1 as well. Okay? The slope over here at like 6 is going to be a shallow value, right? And at -6, I think it's going to be that same shallow negative value. So the same on both sides. So it'd be nice if we could use natural log on both sides. So the way that you fix that, it's really easy. You just do the natural log of absolute value of x. Because now if x is on the left or on the right, you have the same thing. So really all you're doing is you're using the positive and negative values together. So the antiderivative of 1 over x dx is just the natural log of absolute x plus c. Okay, so if you have x to the -1, just remember you're doing natural log, and make sure you have those absolute value signs around whatever's on the inside there. Nice. All right, who remembers our trig? So let's see if we can remember what all these guys are. So antiderivative of cosine should just be sine x plus c, because the derivative of sine is cosine. Antiderivative of sine, negative cosine x plus c. That seems kind of backwards because when you do the derivatives, it's the other way, right? Derivative of sine is cosine, derivative of cosine is negative sine. But if there's no negative here, we have to have it here because that's going to undo when we take the derivative. Antiderivative of secant squared is tangent x plus c. Antiderivative of cosecant squared, that's negative cotangent x plus c. Because derivative of cotangent is cosecant squared, but it's negative, so we have to have the negative there. Secant tangent, that's just secant x plus c. And cosecant cotangent, that's going to be negative cosecant x plus c. This guy, that's the antiderivative of sine inverse of x plus c. This guy is tangent inverse of x plus c. Now notice I don't do the cotangents because if you have a negative here, just pull it out to the front and make the tangent negative. That's how I would do it. You can use cotangent, I suppose, but I would just move the negative out and use tangent. This guy is secant inverse of x plus c. Okay. Good to have those. Your same flashcards you used from derivatives will still work now, right? It's just going backwards. Not too bad. A few more examples. Antiderivative of e to the x plus c, right? Because it's its own derivative. Antiderivative of a to the x. This is weird, right? We've talked about this before. If the derivative is a to the x, like 3 to the x, this came from doing the derivative of 3 to the x. But when you do the derivative, you get that ln a, or the ln of 3, tacked on. So if you do f prime, it's going to be 3 to the x times ln 3. That's a constant, though, so you have to get rid of it. So you divide by ln of 3. Okay, so what we had to do here We say, well, you just divide this by ln of 3. So the antiderivative of a to the x in general is going to be a to the x divided by ln of a plus c. Because when you take the derivative, this is a constant, so pull it out, forget about it. Take the derivative of a to the x, which is a to the x times ln of a. The ln of a's then cancel, and you have the plus c. That just goes away because you're taking the derivative, so you end up with a to the x. All right, I love this problem because it gets three things all together. This one's really good too, actually. So why don't you try those last two on your own and see what you get. All right, let's see how you did. So antiderivative of e to the x, e to the x. Antiderivative of 2 to the x, 2 to the x over natural log of 2. Antiderivative of x squared, x cubed over 3. And of course, you all remembered the plus c. All right, next one. Antiderivative of x cubed, x to the 4th over 4. Antiderivative of x to the negative 1, that's 1 over x, right? So that's natural log absolute value of x. And then this is going to be x to the negative 1 over negative 1 plus c, or you can write it as x to the 4th over 4 minus ln absolute x minus 1 over x plus c. Cool. All right, got a few challenges. So we saw this in the homework the other day. There were some that like chain rule had been done on them, right? If you want to try these, you can pause the video, give it a shot yourself, and then I'll show how I would think through this. All right, let's see what happened. So for the first one, this looks like a 6 was moved to the front. Right? It looks like a 6 was moved to the front and they reduced the power. So right away, I would just see if it works with sine x to the 6th power plus c. Well, the 6 would have moved to the front, would have made this a 5, and then we'd have multiplied by the derivative of the inside function, which is cosine. It works. So this is like, chain rule was done really nicely for you, right? There's no extra constants or anything you needed, just worked out nice. This guy, same deal. The derivative of x squared is 2x. Right, the derivative of x squared is 2x. So this is just the derivative of e to the x squared plus c. They left it alone, and they multiplied by the derivative of the baby, which is 2x. Last one's kind of tricky. 2x is the derivative of the baby function, right? So this had something to do with starting with x squared plus 1, right? Now this 2 on the bottom, so let's rewrite this a little bit different way. This is negative 2x times x squared plus 1 to the negative 2, right? That's what this is. We're trying to find the antiderivative of that. So this negative 2 looks like it was a reduction in power. The negative came to the front, and this was reduced by 1. So I think it's just x squared plus 1 to the negative 1st power. If you took the derivative of that, the negative 1 would come to the front. This would turn to a negative 2, and then you multiply by the derivative of the baby, which is 2x. So another way of writing that is 1 over x squared plus 1 plus c. That's it. Guess I could have the plus c up here as well, but as you're solving it, it doesn't matter as long as you have it at the end. All right, so antiderivatives, not that bad. Indefinite integrals, just a way to say, take the antiderivative and tell me what it is. That's all there is to it. I love you guys. That's why I'm here. Have a great day.